Hello, welcome back on today's lecture, which is going to be on the review of basic vector notations and operations. So this is part of the course for learning machine learning. So let's get started. I'm Professor Wu. Okay, let's start by thinking about vectors. A vector. I hope most of you by now have had some experience with vectors. But let's start from the basics. You can think of a vector as basically a column of numbers, just columns of numbers enclosed in a bracket. For example, here is a column of numbers enclosed in a bracket. So here's the bracket, right? Here's another bracket, right? It doesn't necessarily have to have two or three. It could have any number of elements in it, and each element could be numbers or something else. So for this class, we're going to mathematically and symbolically represent vectors using the lowercase cursive sign. Sometimes they use the lowercase bold as well, so you might see both in literature. But for the most part, we're going to focus on just using the cursive um, font to represent vectors. Now, with a vector, we can denote the length of the vector using this notation. This essentially says that this vector has three elements in there. You see, one, two, three, three elements. And of course, this one says it's a vector with only two elements. The R here stands for real. So it has two real numbers as opposed to imaginary numbers. Hmm? And it's also saying that this vector represents by two number is basically like two dimension. And this one is three dimension. Okay, besides this, right, of course, vectors doesn't have to be just x. It could be basically any letter. Here we use y. We can even use Greek letters. So so we can essentially use x, y, z, any letter, as long as it's lowercase and cursive to represent a vector. Okay, so that is the very basic concept of what vector is. And in machine learning, vectors, we normally use vectors to represent a single sample of data. So let's say we wanted to collect data about Northeastern students. So each student will be considered a single sample, right? So, but with a single sample, you might collect multiple informations about the student, right? We call them these multiple characteristics as features. Features. So a single sample may have multiple features. So for student one, for example, we may be capturing the weight, hair color, eye information. And what we do is we set this as a single vector. So for student one, it will be 160, black and brown. Okay? And for student two, it will be 174, blonde and blue. So you can see that these vectors represent a single sample, in this particular case, a single student, and the elements inside the vectors essentially represent each feature of the sample. A single sample can have multiple features, right? So so you can kind of picture we have a vector, and vectors are normally used to represent a single sample. And then we can distinguish different samples by putting numbers on them. So this is saying the first student, this is saying the second student, or the nth student. Whichever student you are talking about, you can just put that number there. Okay, so this will be the standard we're going to use for the class. This is how we represent a vector, and different samples could be represented using the number subscript. Okay. Once we have a collection of samples, so over here, like I showed you, it's not just one single sample, we have multiple samples, right? Where each first sample is x1 and second sample would be x2. When we have multiple of them, what we like to do is to stack them together. So over here, 154, notice I stacked them together. And 223, I stacked them together. Now, This right here, when we have more than a single column, where we have multiple columns, this right here is the matrix. So X is a matrix. And notice that we tend to represent matrix with a capital letter, capital. As opposed to a single sample, we will tend to represent those as lowercase, lowercase. Hmm? Also, when we're talking about a single sample, the standard we're going to use is going to be a single vector, column vector specifically, column. However, when we're talking about the whole database, like all the samples together, then we're going to stack them horizontally. Horizontally. Notice how as a vector, we're going to always assume it's a vector, a column vector. But when we're stacked together, we're going to assume they're organized in a way so it's horizontal. Okay, so this is a key standard that is used a lot, and you need to make sure you remember that. Okay, more notations on the data. So, like I just told you, if you have the entire data set, we tend to represent them as a matrix. The way we can denote the dimension of the matrix is X has n rows and d columns. So there are n rows and d columns. That's how you know the dimensions of the data. Once you have the data, you can also denote a very specific element. So for example, you can do xij. So I is saying it's the first row, j is the second column. So it's talking about this one. So x12 is equal to 0. Alternatively, you can refer to an entire column. So entire column here is x entire column, and it's saying the third column, 1, 2, 3. So it's talking about this column. Notice how this dot, this colon, basically tells you you're taking the whole column. Or you can, denote the entire row. So over here is you can use that notation, except the colon is at the back as opposed to the front. And this is saying that you want the ith row. Now, there are two ways to represent this. General, we just write xi, lowercase. Or you can write it this way. They mean the same thing. So x1 is essentially saying it's the first sample. And here is horizontal. Once again, when you're just talking about a single sample, it is vertical. Okay. Now, in machine learning, it's really, when it comes down to it, it's all about the manipulation of data, either as vectors or matrices, right? That's basically all we're doing. We somehow represent the data, do some kind of calculus on them, calculation, and then we're done. So the first step for us to learn machine learning is to really review and understand the basic matrix and vector operations. Now, I assume a good deal of you guys have already done this. And for those of you that haven't, don't worry. Well, we'll spend a class to kind of review these concepts. So let's start. And luckily, none of them are really hard. For example, addition and subtraction. Addition and subtraction is really easy. Let's say you have a vector x and a vector y. So what happens when you try to add them together? Well, when you want to add them together, you just match up the element and add them together. So 1 plus 2, which is 3, 3 plus 2, which is 5. So adding them together is not a big surprise, right? And visually, what's happening is if you have 1, 3, which is this vector, and then 2, 2, which is this vector, your final vector is 3, 5, which is talking about this one right here. So that's what's happening visually. But mechanically, what are you doing? You're really just adding the elements together. And subtraction is the same idea. So if you have x minus 1 instead of plus 1, then it'll be 1 minus 2, which is negative 1, and 3 minus 2, which is 1. So subtraction and addition of vectors are really, really simple. Now, another operation is called the transpose. So if you have an x vector, x transpose it's telling you that whatever is in the column form, turn it into a horizontal form. Right? Another example is y, the y transpose t, transpose, right? So if it's transpose, it converted. Now, if for some reason a vector is in the horizontal form, which it shouldn't be, but let's say for some reason it is, and you write the transpose of this, then the transpose becomes column. So column becomes row, row becomes column. That right there is the transpose operation. Next is multiplication. There are multiple ways to do multiplication, and there are different products, right? So one of the product is called a Hadamard product. The symbol for Hadamard product is you take x times y. This is how you do multiplication: a circle and a dot. And the Hadamard product is basically the same as addition and subtraction. You take this, you match up the elements, you multiply them together. Here's 2. You take them, you multiply them together, that's 6. Right? So the Hadamard product is really just an extension of the addition, subtraction, extended to multiplication. Now, another one is called the dot product. The dot product is written this way: x dot y. However, an alternative way to write it is x transpose times y. Okay? When you have this x transpose times y, what you do is you multiply this with the first element, you multiply this with the second element, here and here, and then finally you add everything together. And this is called the dot product. After you add everything together, you should get 8. So the dot product is very, very similar to the Hadamard product. Right? We also take one element, multiply, and multiply. The only difference with the dot product is once you have this final product, you add all the numbers together, resulting in only one number. 6 plus 2 is 8, right? So, so another thing that's different is the notation. We write them as x transpose y. Okay? If you have x and y, that doesn't make sense. It has to be a transpose. Okay. Later on, once we get to matrix, you'll see why that notation makes more sense. Okay. Now, another thing is called the inner product. So we learned the dot product. Well, inner product is notationally written this way with 2 brackets like this. Now, with this inner product, for our purpose, you can treat it to be identically the same as the dot product. So you can see now it's exactly the same. So when you see this notation, or this notation, they're all the same. And they are all 3 of them are used like quite regularly. So once again, Hadamard product, you take element and multiply them together. The dot product, which is written this way, most commonly written this way, it's basically the Hadamard product, except you add everything up in the end. Okay? And the inner product, you can treat that as the same as the dot product. Okay? So now that we did 3 products, there's a 4th one. We just did the inner product. Now there's another one called the outer product. The outer product, remember the inner product is x transpose y. Outer product, which uses this symbol here, right? This is the outer product symbol. Notice how the transpose is on the outside, right? The transpose is not in the inside anymore. It's on the outside. Therefore, when we write them together, when we essentially is have a column and a row. Now, the outer product, the way we would do this is we will take this element, multiply by the column, which will give us this column. And then we'll take this next element and then once again multiply by the column. So we got this. So the inner product and the outer product have different operations where the outer product, essentially you take this, multiply, this, multiply. The inner product is like a Hadamard product. You multiply one element at a time and then sum them together. Yeah. Multiplication by a constant value. So if you, like right now we talked about vector multiplied by vector. What if it's just a vector multiplied by a number? Well, if it's a vector multiplied by some number alpha, for example, you simply take this number and multiply one at a time. So it's alpha times x1, alpha times x2. For example, if you have 3, well, it'll be 3 times 2, 3 times 1, giving us 6 and 3. Okay. Next, just like vectors, when we talk about matrices, we can also transpose them. So over here, we saw how you can transpose the vectors, which converts a column into a row. A row convert into a column. Now, what about a matrix? How will we transpose, for example, this one? Well, it's actually really easy. You simply convert all the columns into row. Okay, so over here, well, you take this column, convert it into a row. This column, convert it into a row. This column, convert it into a row. And that's it. That's it. This is that easy. Now, if you put a transpose here, you will convert back. Okay? So you will convert all the rows to columns and columns to rows. And over here, notice how if you do a transpose and a transpose again, it's identical to the original. Okay, so that's essentially how you can do it. You take each column, convert it into a row, take the next one, convert it into a row. So that's what the transpose is for. Now let's take a little bit of time. Why don't you try to solve these following equations using everything we've learned so far? It takes a while. It takes a while to basically absorb. Ooh, I just jumped somewhere. It takes a while to absorb all this information, and it takes repetition. Like you just got to do a couple times, and then you'll get it. So take 10 minutes, pause the video, make sure you can do this, and we'll move on. Okay. So, all right, pause the video because I'm moving on. I wrote the solution out for you for each one of these, so you can essentially go and double check if what you've done makes sense. So these are the solutions. Okay, so now let's continue with products, multiplication. We talked about multiplication between vectors, but now what about multiplication between matrices? So for example, here's x and z. We want to do a Hadamard product. Remember, this is the symbol for Hadamard product. Well, Hadamard product was the one where you match up the element and multiply them together. So over here, you match them up, you multiply them together. 1 times 1 is 1, 0 times 3 is 0, right? 2 times 2 is 4. So you just match them up and multiply them together. The Hadamard product is really, really simple for either multiplication or vector multiplication. However, um, um, it gets a little bit harder when we're doing other products. So over here is an example of a Hadamard product, right? And then multiplied by a constant. So here, if you have a constant multiplied by a matrix, you may have guessed at this point, you simply take this and multiply by every single element. So once you do that, you have this, and then you do the Hadamard product, which is when you align every single element together. Okay. So, like I just showed you, if you have a multiplication of matrix by a constant, then you simply, like 2x, you simply take the 2 and multiply by the entire matrix. Now, when you have an addition, for example, you have a matrix like this, and you're trying to add to just a number. So if you have matrix adding to a number, the standard we're going to use here is you simply take the number and add it to every single element. So just add 2 to this. So 2 plus this will be 3, 2 plus this will be 2, 2 plus 2 is 4, and 2 plus 1 will give us 3. Okay? All right, the next one is called a matrix dot product. When we have the matrix dot product, then let's see. It's written as this. The matrix dot product is probably the most commonly used multiplication. And therefore, the standard is you don't even need to write anything. You just write xz. And that assumes that we're doing a matrix dot product. And how does it work? Well, what we do is we take the first column and multiply by the first row. So this right here is your dot product. Okay, so you do the dot product between the first column and the first row. And then you do the dot product again between your first column and the second row. And then you can do the dot product again between your second column and first row. And then finally, you do the dot product here. Remember, when we had the dot product, we always treat this as the horizontal. Well, this notation carries over here. So you take the column and you multiply by the row. And once you calculate the dot product for each one of them, right, this will yield number, you number, 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 which give us your final result of a 2 by 2 matrix. Okay? Let's do another example. So let's say we have this matrix and the multiply by z, xz. So what would you do? Well, you will take this and to the multiply by the first row. So this will give you 1. And then you take this again and multiply by this using the dot product. So 1 times 2 and 2 times 1. Add them together is 4. Okay? So this is how you essentially calculate the multiplication of matrices. Now, a quick aside: this is a very useful property of the if you have a dot product between x and y, and if you're trying to find the transpose of the result, this is equivalent to multiplying the transpose of y times transpose of x. So notice how you rotated the two of them and then add a transpose on this. Okay, so this is a property which we'll go over, return to over and over again. All right, so another property we need to learn is that the order of the matrix of dot product cannot be flipped. What that means is if you have x times y, if this is x and this is y, this is not the same as y times x. You can test this out. You just multiply x times y, and then you multiply y times x. And you will notice that the results are not the same. Okay, so you cannot x times y when you do a matrix dot product is not the same as y times x. Cannot flip this. Okay, the diagonal and trace of a matrix. So matrix, you can extract various information out of it. One of it is the diagonal. What is the diagonal? Well, if you have a square matrix like this, the diagonal is simply the diagonal element. Okay, so the diagonal of this matrix is a vector 1, 4, and 9. Notice how this is 1, 4, and 9. Here's another example. The diagonal of z is simply 4 and 1. Okay, diagonal is always this way. It is never this way. Not that diagonal. The diagonal is always this way. Okay, now when we talk about the diagonal, we got the diagonal. When we talk about the trace of the matrix, so if we have a matrix and somebody is asking you what is the trace, well, the trace is simply the diagonal, right? And you sum up all the elements. So right here will be 149, 149. So you take the diagonal and you sum them up, which gives you the trace. Okay. Next is the matrix inner product. So we did the matrix inner vector inner product. The matrix inner product is when you have x times the transpose of y. Okay, so this right here is the dot product. X dot product the transpose y, and then you should have a square matrix, and you take the trace of that. We just talked about what trace was, right? You had diagonal, which gives you the diagonal, and then we had the trace, which sums up. So the inner product is kind of accumulation of everything we learned. To do an inner product, you need to know how to do transpose. You need to know how to do matrix multiplication. And then you need to know the diagonal of this matrix because trace is the summation of the diagonal. So if you can do the matrix inner product, that in itself is essentially like everything we've learned. Okay, and the way we will write this, you can see you multiply the two matrix together. You take the trace to transpose. Once you have the transpose, you can multiply them together. After you multiply them together, you simply sum up the diagonal to get the trace. And that's how you get the matrix in a product. Okay? All right. So let's spend a little bit more time now to kind of exercise your muscles so that you have the chance to kind of absorb because we're doing this really quickly. And I can talk here all day, but not until you get to do it, you won't. It's not nothing's gonna really stay. So give it a try and see if you can solve these problems. Right? As and if you have time, solve for these. Okay, pause the video and give it a try. Hopefully you're able to. Hopefully you're able to get it. Over here, I have the solutions for you, so you can go and kind of study to see if you did it right or you did it wrong. Okay, so these are all the solutions. Make sure you are able to solve them. Okay, so I'm moving on. Like hopefully you pause the video and you have already gone through this already. Okay. All right. So now that we've gone through the mathematics of it, we also in real life, obviously you don't want to be calculating all these stuff by hand. What you want to do is have the ability to calculate them in the computer. So, whoops, what just happened? So what we traditionally have been using is this tool called Python and NumPy. NumPy. Okay. And once you have NumPy installed, you are able to represent vectors, matrices together and essentially calculate various information about them. So, for example, over here you have a vector, right? So you can write this vector this way. Notice how each column is represented by a bracket. So that's a column. I mean, each row is represented by a bracket. So that's 1 and 2. Over here, you can represent a horizontal vector by writing it this way. So you can represent either a column vector or a horizontal vector. You are not going to need this very much because we normally represent things as a column vector. It's very rare you're going in this class you're going to be represent things anything in terms of or horizontal vector, right? Over here is another way to denote a vector, and it's essentially just saying P is an array, right? That's all it's saying. What is magical is once you have defined these variables P, V, U, and P, when you want to do addition, subtraction, you simply write V plus P, right? Which will create the operation, and you will see that V plus P will give you the result here. Or you can do the dot product. So you take V, remember you have to do the transpose, and then you dot P, and this gives you the result, V dot P. You can also denote matrices. So over here is a matrix, right? Well, you have this matrix here, so it's now defined. A is equal to this. Once you have the matrix, you can get the entire row, entire column out of it. So over here, you can get the entire row. Now, notice this says 0. So instead of starting from 1, the first row, it starts from the 0th row in programming. Since most of you are CS students, you should be used to that. That in mathematics, we start from 1. In code, they tend to start from 0. Or you can get the second column. So this is 3 and 4. So it's getting the column. Remember, 0 is the first one, and 1 is the second one. Once you have the vector and the matrix, you can run various other operations, such as max. So this gives you the maximum value in V, which should be 2. See? And the max value in the matrix A, which should be 4. Okay? Or the minimum value in A, which is 1. Or you can even find the average, right? What's the average of v, which is 1.5? Okay. Now here is some code examples. So here's the vector v, right? I can represent v that way, and then I say that I can print out the v, so you can actually visually see it. I can print out the u, exactly the same. Here's the A matrix we talked about, and we can do this one is the outer product. Here's an example: u dot v transpose. Remember, the transpose is at the outside, which is the outer product. Outside, outer product. We can also do the inner product, which the transpose is inside. And then you can also do like more complicated v transpose a v, right? So this is multiplied by a matrix and then multiplied by vector. So yes, you can multiply a matrix by a vector and vector by a matrix. Or you can do a Hadamard product. The Hadamard product, remember it was this symbol. In Python, it's simply a star. You write a star and that does the job. Here's an example of a trace. Right, so this right here gives you the trace. Okay. Now, try to consolidate your knowledge by solving these by hand. Hopefully, at this point, you've had a little bit of practice, and solving this will be a lot easier. Okay, and like solving this by hand is not fun, so you can always confirm. Like there's no solution to these ones, so you want to confirm this by typing these into the Python. Okay, so that's the final exercise of the day, and I will see you in the next lecture.